A very warm and pleasant good morning to all the honoraries, dignitaries, and delegates of eSESTEC 2020. Welcome to all of you at the third day of eSESTEC 2020. Today we have 4 technical sessions and 1 poster session. There are few important announcements before starting the session. All the participants are requested to switch off their video. Also, if participants have any query regarding communication or talk, they can write in the chat box of the host eSESTEC 2020. On the behalf of organizing committee, I request Professor Vivekanand Kane to chair the session. I take this opportunity to briefly introduce Professor Kane. Professor Vivekanand Kane is an outstanding scientist, AD, Material Group and Head, MP and CD, is from the 29th batch of BRC Training School. He is an expert in the field of corrosion, stress corrosion cracking and irradiation damage of stainless steels, nickel and zirconia in stainless steels under reactor operating conditions. He has played a pivotal role in the development of radiation and corrosion resistant stainless steel for reprocessing and waste management plants, failure analysis and material selection for various units of DAE. He has 65 publications in peer-reviewed journals. He is a recipient of several prestigious awards, including Metallurgist of the Year 2011 from Ministry of Steel, Government of India, DAE SRC, Development of Atomic Energy Science Research Council Project Award 2008, Homi Bhabha Science and Technology Award 2005, Meritorious Service Award by NACE International Gateway India Section 2011. So I request Professor Vivekanand Kane to kindly chair the session.
Thank you. It is a pleasure for me to chair this session and welcome all the participants for this conference. Today, the first session, we have with us 2 plenary talks. The first talk will be given by Professor Kamlesh Sarkar and the next one by Professor Vikramasinghe. I very briefly would introduce the first speaker for the plenary talk, Professor Kamlesh Sarkar. Professor Sarkar is a distinguished professor of chemical engineering at the New Jersey Institute of Technology. He had got his PhD from University of Illinois, authored 212 refereed journal papers, 25 book chapters. He has received a number of patents, 35 in US, 3 in Canada, and 1 in India too. He is widely cited. His sketch index is 61. We are indeed honored to have Professor Kamlesh Sarkar to deliver the plenary talk on the topic of a few recent developments in membranes and membrane separations. Professor Sarkar, you will have 35 minutes to deliver the talk, and after the talk, we will have around 5 minutes for interaction with the audience. Professor Sarkar, please. You are muted, sir.
Professor Sarkar, you are muted. Kindly unmute yourself.
Yeah, I have unmuted myself. Let me share the screen. Are you guys able to see my screen now?
No, sir.
I thought I shared it.
It was initially got shared, but then unshared. Yeah.
Now, are you able to see it?
Yeah, I can see the PPT, not the slideshow.
Okay, is it gone into slides now?
Yeah, perfect.
Okay, good. All right. Good morning to you. All the attendees there. It's pretty late in the night in New York right now. It's 11:40 p.m. in the night, but it's early morning in India. So let me start my presentation by greeting all of you and organizing this very interesting conference focusing on separations. So as you know, separations primarily deals with either gas or vapor mixtures or liquid solutions or suspensions. And each of the sub areas are very, very involved, and there are all kinds of developments taking place. So I'm going to talk to you about a few areas, and these are the three areas that I'm going to talk to you about. These are disparate areas, but each area is very important, and there are all sorts of new developments taking place. The first topic I wanted to talk to you about involves reverse osmosis separation of organic solvent mixtures. This is not very common. A lot of people have tried it in the past, distant past, but there has not been that much of progress. But recently there has been some interest, so I will talk about what we are doing, and we are achieving extraordinarily interesting results. Then I will talk about graphene oxide-based membranes as barriers against toxic vapors and gases that would be needed to protect oneself against exposure to toxic vapors and gases. And then I will talk about direct contact membrane distillation studies primarily for desalination purposes. So let me start talking about reverse osmosis-based separation using perfluorocopolymer membranes. And these perfluorocopolymer membranes are quite unusual in nature. It is not as if that they are not known. A lot of people were studying their separation properties of gas mixtures and vapor mixtures, but very little was done in terms of studying the separations of liquid mixtures. And we started studying some of these properties using the process of evaporation at the MAST Center that Professor Vikramasinghe is going to be talking to you about. And we started seeing interesting things, and I switched quickly to organic solvent nanofiltration and reverse osmosis, and we have gotten extraordinary results. So what is very interesting about these polymers? First, they have very high fractional free volumes in the range of 0.32 to 0.37. Remember, most polymers, fractional free volumes would hardly exceed 0.10 or 15% or maybe 16%. And as a result, it has very high permeance for oxygen at the level of 1500 to 10,000 GPU, and yet they have significant selectivity. When you have 1500 GPU, the selectivity is 2.6, and you still have selectivity of 1.7 when you have 10,000 GPU. Their average free volume dimensions are around 5.9 to 6.4, so pretty open. I'm coming to it in the next slide in greater detail. They're very hydrophobic, and the fractional free volumes of Teflon AF-type membranes, AF1600, AF2400 are also very high. Now, CMS3 and CMS7 are also AF-type membranes. There may be a little bit of a variation in terms of the dioxyl content in this copolymer. And the membrane that I'm focusing on is CMS7, has 90% dioxyl content, and the rest is PTFE essentially. These polymers cannot be dissolved by any solvent except perfluorosolvents. And we have studied their swelling in all sorts of solvents, including DMSO, DMF, NMP, etc. And it's less than 2.5%. And so those are very useful for the purpose of separation of organic solvent mixtures. And I'm repeating that information at the top left part of this slide. The CMS7 has average free volume radii of 5.9 to 6.4 angstroms. Corresponding radii estimates in normal glassy polymers are going to be around 3 to 4 angstroms at the most. And interestingly, most organic solvents, if you think in terms of their diameters, by assuming these are spheres, that's around 5 to 7 angstrom. They'll slip through CMS7 without much diffusivity-based selectivity. And need I remind you that selectivity of separation through a polymeric membrane is usually considered to be a product of diffusivity, selectivity, and solubility selectivity. So if in fact we have such large free volumes, dimensions, and we have such large fractional free volumes, how can you have any diffusivity-based selectivity? These molecules are just going to slip right through every one of them. And so selective sorption potentially could be very interesting. And there have been some studies that were initiated in the last 15, 20 years, quite a few studies. And they have been looking at the free volume size distribution using PALS technique and so on and so forth. So my information regarding the average free volume dimension 5.9 to 6.4 is based on some of those studies. On the right-hand side of this slide, I'm showing some recent results from Georgia Institute, where they have been studying as part of a historical work done by Bill Corus, carbon molecular sieves, where the opening dimensions are quite controlled and very little variation. So they took a 50-50 mixture of paraxylene and orthoxylene, and they were able to show that 50-50 mixture could, under pressure, give you as much as 81% paraxylene in the permeate. If you take a 90-10 mixture of paraxylene and 10% orthoxylene, then you can get 97-98% paraxylene at say 60 atmosphere pressure. So these are this is a background of sorts. There are other membranes that are being studied, but let's continue with these hydrophobic membranes. So if in fact you are going to have an organic solvent reverse osmosis, and if you have a mixture of two organic solvents, let us say toluene and NMP, you know, the osmotic pressure of the solution is determined by the solute concentration, the solute that is being rejected. And so if we use Van 't Hoff's equation, which has been found to be reasonably good for dilute solutions, even organic dilute solutions, so 90 weight% toluene, 10 weight% NMP will have osmotic pressures around 2200 kPa. Now, in our case, we have gone and studied only up to about 5000 kPa plus. We didn't go to very high feed pressures. And so as a result, we are going to be limited in terms of the areas that we have explored. Now, volume flux in reverse osmosis, if you look at the bottom of the slide, is proportional to the pressure, applied pressure difference, delta P minus sigma times delta pi. And sigma is, of course, the reflection coefficient is supposed to be 1 for a perfectly rejected solute. And LP is your permeability coefficient. So here we are showing data on a mixture of toluene and NMP. So if we have 95 weight% toluene in feed, 5% NMP, or 90 weight% toluene or 75 weight% toluene, and if we apply appropriate pressure, what we see is that the permeate that is coming out has pure toluene in the permeate. And we were surprised and very, very shocked at this because this is unusual. Of course, the fluxes are somewhat on the low side. You see the pure toluene fluxes are significantly higher. That, of course, reflects the fact that we have a significant osmotic pressure. But we are getting pure toluene in the permeate over this concentration range. Let us look at the next one. This is a mixed behavior of the mixture of toluene, DMF, dimethylformamide. And here, all the way up to 50 weight% toluene in feed, we see that the permeate that is coming out is almost, not almost always pure toluene. And we see a linear behavior in terms of the permeate flux going up as the pressure difference is going up. So these are interesting, unusual, and unexpected behavior, and we started wondering, what does literature tell us? But before I go into that, I wanted to show you something. We took this polymer and soaked it for 14 days in feed mixtures that contain either 90% toluene, 10% NMP, or 90% toluene, 10% DMF. And then took this polymer out and put it in a headspace device connected to a GC gas chromatograph and stripped out the sorbed solvents at a high temperature. And what we found out is that the sorbate was 100% toluene in both of these cases. In other words, toluene is not allowing NMP and DMF to be sorbed in this particular polymer. This is a phenomena that we will see repeated with various other compositions that we'll talk about. Now, if I can recall some of the very basic conclusions that are known to membrane scientists and engineers, is that if you take Spiegler-Kedem model for reverse osmosis, you achieve a very high solute rejection when you go to very high delta P, and that value is equal to the solute reflection coefficient. If you use irreversible thermodynamics models, you see at very high pressures, you achieve a solute rejection that's 1 minus the solute partition coefficient. In our case, if the solute is being rejected completely, sigma j would be equal to 1 and kappa sub j is going to be 0. So we'll be having a rejection of 1. But interestingly, we achieve that rejection of 1 at very low pressures. And other models, whether it's Downfall's model or others, they're not valid because those are for swollen polymers. We have very little swelling. The model that was developed by Wymans and Baker for ultramicroporous membranes in gas separation using PTMSP, which has probably the highest free volume, just slightly larger than CMS7 that we are working with. In that case, they found out that if they had 1% freon in nitrogen, that freon will condense, probably in multi-layer in the free volume regions and in the transport corridors. And they're going to block out nitrogen permeability very substantially. Now, we haven't gotten or seen any such results in our case. If we have 1% concentration of a species, we don't see any specific effect. So we are forced to conclude that in our case, selective sorption of one solvent species in the free volume elements of CMS7 to the complete exclusion of other species is creating an environment of total exclusion of the non-adsorbed species from permeation. Here we are showing some results with methanol NMP and methylpyrrolidone. Interestingly, these are both extremely polar. Methanol is protic, NMP is aprotic. Interestingly, also the polar component of solubility parameter for both of these solvents is identical, 12.3. They're very polar. Yet, when we subject this polymer to this particular mixture, solvent mixture, for 75 weight percent methanol in feed or 90% weight percent methanol in feed, we see pure permeate of methanol. We see a similar behavior when we have methanol DMSO. Both are highly polar, yet 90 or 90 weight percent or 95 weight percent methanol in feed gives us pure methanol in permeate. And the conclusions we have were reinforced when we did some sorption studies. And we took 90% methanol, 10% NMP, and we studied sorption behavior and then dissolved it in a headspace apparatus at a high temperature. We found out the sorbate is 100% methanol. How come? And so what we have seen in the literature is they have looked at other perfluoropolymers and they have seen that when you have pure alcohols, the transport of these pure alcohols through that polymer can only be explained by assuming that these guys are dimerizing. And so I've shown the model of two methanol molecules dimerizing, and so at their end they have methyl groups which can accommodate themselves very easily in the hydrophobic free volume cavities of this polymer. And so methanol is able to dimerize and go ahead and occupy the free volume space. NMP does not have that capability because NMP is aprotic. And we see similar behavior in mixtures of ethanol and NMP. We are seeing ethanol 90% or 95% in feed is yielding pure ethanol in the permeate. On the other hand, when we have 5 or 10 weight percent ethanol in feed, the bulk of the liquid that is exposed to the polymer is NMP. NMP cannot dimerize, and neither is ethanol, because ethanol is not contacting the polymer that much. And so therefore the permeate is essentially the feed mixture. There is no separation at all. And we see that concept reinforced when we take a 90 volume percent ethanol, 10 volume percent NMP. We see that the sorbate is 100% ethanol. And we have to do it for other compositions, and we should be doing that as we go along. Here we have a different mixture, but same thesis. Ethanol DMSO, high ethanol concentration, pure ethanol in the permeate. Now I have a very different system. I have ethanol and butanol system. Both are protic. Both can dimerize for that matter. And lo and behold, what do we see? If we have 98% ethanol in feed, my permeate is pure ethanol. If I have 98% butanol in feed, I have pure butanol in the permeate. So both have capacities of dimerizing, which other people have seen, but the dimerization tendency decreases as you go to larger and larger hydrocarbon ends. So if you go to C6, C7 alcohols, these dimerization tendency essentially disappears. Also, you may not be able to accommodate them in the free volume dimensions that are available in this particular polymer, copolymer. And so we also checked the sorption behavior. If we have 95% ethanol, 5% butanol, sure, the sorbate is 100% ethanol. But if we, on the other hand, have 5 volume percent ethanol, 95 volume percent butanol, sorbate is 100% butanol. When we have 50-50 mixtures, it's a 50-50 sorption. There is no difference. So I'm not going to show any more results that we are trying to develop, but I'd like to point out some conclusions that Yampolsky, who has been studying these polymers for a long time, said that these polymers exhibit unusual thermodynamic properties. They have different sorption selectivity than hydrocarbon-based common polymers. And so similar solubility parameters should lead to a certain miscible behavior that is not true for PFP solvent systems. And lots of general attempts have been made to develop a model for these things. So far, nothing has appeared. And I would leave this topic for now. It's very interesting, and the experimental results that are coming out are very, very interesting and certainly of extraordinary industrial significance. I'm going to switch the topic to something totally different. We are going to gas vapor mixtures in the presence of humidity, and so we'll talk about graphene oxide-based membranes as barriers against toxic vapors and gases. So if you think about these for garments or masks or things of that sort, what is commonly done is you employ an extensive amount of sorbents, active carbons. Sometimes they're impregnated with metal salts for gas-solid reactions. But these garments are very bulky. And so the question that was posed to us is, can you build a protective fabric or barrier, a membrane in our mind, against chemical and biological threats, completely block these agents? And the protective fabric should be breathable with good moisture transmission, low thermal burden, and good mechanical properties, etc., etc. And I'll show you some of the progress that we have made. So one of the very interesting things about graphene or graphene oxide-based laminates that people have been studying for the last about 10, 12 years is that the conclusion is major transport pathway for gases or vapors is structural defects within the geoflake instead of spacing between geoflakes. You can have very high selectivity. There are particular studies of selectivity for hydrogen over CO2. in certain geolaminates. The other thing is the hydrogen and helium permeances decrease exponentially as the membrane thickness is increased. And of course, you have to support such a laminate on a support membrane. Preferably, it has to be a porous support membrane in general. And so what was done by our graduate student, dispersed a certain amount of geopowder in DI water in the presence of some STS and sonicated quite a bit, and then added some EDA, which is ethylene diamine, because that is going to be used to cross-link contiguous layers because of the polar functional groups that are sticking out at the edges of graphene. And so a certain amount of EDA is dispersed in that solution, and then you filter this solution over a porous polyether sulfone or a porous polyether ether ketone membrane by vacuum, and then you dry the membrane and physically compress it because there's a lot of unevenness. You would like to reduce that, and then heat the membrane to 80 degrees to create cross-linking, and then spray on top of that with a little thin coating of polyurethane to make everything handled very easily so that the membrane could be bent and folded and used. And so then we studied the permeation of various gases, vapors, and water vapor through this membrane using two different types of apparatus. This dynamic moisture permeation cell is where you have the humidified or non-humidified feed gases going on top of the membrane. And in the bottom, you have helium stream, which is picking up whatever is permeating through the membrane and going into the gas chromatograph. Another study, another method to study the permeation is you have a membrane. At the bottom of that membrane, you have a reservoir of the liquid whose permeation as a vapor you are studying. And then at the top, it's open to the atmosphere. And you keep this essentially in a desiccator where, for example, if moisture is coming out, the moisture will be absorbed by the desiccator. Every day you weigh this plastic container and see what kind of weight is being lost. If there is water, if water is evaporated, its weight would be decreasing. And so we did that for water, toluene, and a few simulants for various bad gases. So DMMP is a dimethyl methyl phosphonate, is a simulant for sarin, and that is the type of membranes that we were preparing. And after all of the things are done and a polyurethane coating is there, you can bend it easily quite a few times without affecting their permeation properties. And these are giving you some FTIR spectra of the cross-linked geomembrane. And these are XRD for the geomembranes, and we have gaps that are quite intense in the 0.4 nanometer range, which is the normal gap that we should have in a graphene or geo laminate. However, because of N groups on the edges and so on, you have other gaps. These are some of the other gaps in our laminated membrane. And so here are some data showing blockage of DMMP and toluene, whereas water vapor is freely permeating. If you look at that so-called upright cup method, where you had a layer of liquid at the bottom which was evaporating, the weight of that cup was decreasing linearly with every single day. Whereas if we did that experiment with pure DMMP liquid, the weight did not change at all because DMMP was not able to go through the membrane at all. The same thing happened with toluene. Toluene was not able to go through at all through this, whereas water was continuously disappearing. And when we had a 15-day experiment, DMMP would not be able to cross it for 15 days, and water vapor, of course, disappeared, and we had a dry stuff. So DMMP dimensions would potentially be blocked through the defects that we had seen. This particular table shows that you can have a bent membrane or a non-bent membrane, the permeance and the selectivity of the gases are very, very similar, very similar. This particular slide represents your moisture vapor transmission, because moisture vapor transmission is very important. It is suggested that these barriers better be able to transfer at least 2,000 grams per meter square per day of moisture before it can be considered as a breathable fabric. And our system was showing more than 3,000 grams per meter square per day. So that's very good. And then the experiments were done with a simulant for sulfur master, which is 2Cs. And what one sees is that for the first 16 minutes, nothing came through. And after that, there was a steady permeation for a long length of time. Experiments were stopped here at the level of 2 milligrams per meter cube of Cs. When the full concentration that is being used, if this had no blockage capacity, this membrane here, it would be 12 milligrams per meter cube. So we were having 98% plus a rejection of this. And so that's a good start. And we are looking at other ways to improve such behavior. These membranes also have significant tensile strength so that they can be bent and used for very practical purposes. And I just wanted to tell you that this is an interesting area. Not that it directly affects today's overwhelming consideration with COVID-19, but it certainly has a lot of relevance, especially for situations dealing with industrial accidents or any other kind of warfare situations. I'm going to focus now on the third topic, again, very, very far away from this second topic. This is direct contact membrane distillation studies using primarily hollow fiber membranes. Some of you may be aware that if you have a porous hydrophobic membrane, something like a Gore-Tex membrane, and then you bring hot brine on one side, and at atmospheric pressure, the hot brine cannot enter these hydrophobic membranes. And if you keep cold water on the other side, and from hot brine, you'll have water vapor evaporating, will come and condense in the cool distillate. Professor Vikramasinghe is going to go into details of many studies that he has done. And I'm going to talk about something slightly different in terms of the challenges that we are trying to overcome. You can also have vacuum pulled on the other side instead of having a cold distillate. So our studies are primarily with direct contact membrane distillation. We have also done some vacuum membrane distillation studies. So the challenge in this is if you're trying to recover 30, 40, 50, 60, 70, 80, 90% water, 95% water from saline water that contains all kinds of scaling salts, calcium sulfate, calcium carbonate, etc. These scaling salts, calcium sulfate and calcium carbonate, they don't have much solubility. So as you start concentrating, they'll precipitate. They'll start blinding your membrane. And many investigators are not paying attention to these things, and that is very necessary. And so what we did was we studied first with porous polypropylene hollow fibers. And a company called Applied Membrane Technology was able to plasma polymerize various coatings of fluorosiloxane coatings on these porous hollow fibers. And the coating scenario that we adopted is where the surface of the pores of the substrate is not covered. So in other words, you have a larger pore diameter of the coating. So this was done with very short amounts of plasma polymerization. Essentially, if you weight it even this surface, then they have to come and weight it here, but there are other advantages. So this type of coating with brine in cross flow, this is another important thing. Our hot brine was coming around these hollow fibers. So there were flow separation points all around. And when you have bunch of hollow fibers together, there is an extraordinary amount of interaction. So we had secondary flows cleaning the surfaces of all the hollow fibers at all locations continuously. As a result, we had no problems recovering 80 to 90% of seawater from seawater without much flux reduction. We would go up to 18–90%. In laboratory studies, we used supersaturated solutions. We had precipitates flowing around. The flux was not affected at all. And so these are some of the photos of our devices built with the help of applied membrane technology. So these are the hollow fibers, and the brine was really flowing normal to those. Okay, so here brine is coming in through the top and going through these fibers and going out. And so we had a pilot plant that was producing close to 0.67 gallons per day. I forget now. I'll give you the exact figure. 0.67 gallons per minute, GPM. So these are some of the fluxes that we were seeing. And these variations are because we were having flow variations. And so when the flow varies, the water flux goes up if the flow increases. And here we are around 18 to 19% salt. And so there was too much precipitate and we shut down the system. All I'm trying to point out is this has been done now with very large modules in a steady state fashion. We ran the system for 5 days as we were concentrating the stuff, and we had no salt leakage at all. And the basic conceptual scheme that we were using is this. So if we had, say, hot brine at 90 degrees centigrade coming in, it's getting cooled down to say 35. It's come in here, a little bit of fresh brine is added, and then you send it to a heat exchanger. The distilled water that has collected the water vapor gets heated up to maybe say 85, 88 degrees centigrade. You bring in this heat exchanger on the other side, you recover all that heat in this brine and reheat the brine to say 85 degrees if you can. And so all you have to do is supply 5 degrees centigrade worth of heat from 85 to 90, and then you are able to evaporate 55 degrees worth of water from the brine. So you can easily have 10 pounds of water evaporated per pound of steam that you're supplying. And we actually achieved results that are not too far from these in our laboratory. I'm going to show you another potential example. There are, of course, produced water everywhere, wherever there is oil extraction going on. And after you take out the hydrocarbons from that produced water through various types of flotations or other things, and then there are actual plants. This is the OPUS technology. That would ultimately have reverse osmosis units at that end and recover a very significant amount of water. And so we were essentially supplied by Chevron company, this water coming right out of here. And this was sent to us, but this water is hot. This is at 70 or 80 degrees. And so in the process, they cool it down. This is the heat exchanger. This is the heat exchanger. And so in our case, we took that water that was shipped to us in 55-gallon drums and just replaced all of these by just our DCMD unit. And we were able to show for 3 different levels of feed concentrations that we were able to recover 80% plus water without any physical fouling of the membrane. We had precipitates floating around. And you can see the quality of the treated water. This is on the distillate side, and this is on the feed side. So people talk about silica. No silica was going through this membrane. And whatever bicarbonate you see is essentially due to carbon dioxide, which is you're dealing with a feed at high temperature. So therefore, you will have certain carbon dioxide come out and collect in the permeate. And the next level of modules, hollow fiber membrane modules have been designed. These are much simpler, lightweight hollow fiber modules that have 5 times more surface area and that do not suffer from the accumulation of precipitates of calcium carbonate and calcium sulfate, which is what will happen in regular hollow fiber membrane modules. These are our new designs. And so this we have already studied and published these, and Applied Membrane Technology is going further in terms of additional studies after we showed something else. Namely, we can take simple hydrophilic flat films and we can have a very light plasma polymerization of fluorosilicon coatings. If you do more plasma polymerization, the pore opening is going to be reduced even further. You can go even further with longer plasma polymerization. But in general, we would be limited to here or here. And when you do that, the gap, the gas gap through which the vapor is being transmitted is very small because all of this is wetted by water. This is a hydrophilic membrane. So the distilled water on the other side is present all the way up to here. You have a very small air gap. And so there are other advantages in terms of uh, conductive heat loss and all sorts of things. And we showed that you can have extraordinary fluxes with flat membranes. And so here at 60-degree brine temperature, using just regular PVDF hydrophilic membranes with a little bit of a coating, which gives you a liquid entry pressure of 16, 17 psi, we can get fluxes of 50, 55 kilograms per meter square per hour. This is huge. And now that is now being tried now with polyether sulfone-based coated hollow fiber modules. And these modules were developed and studied at Applied Membrane Technology. And so what you see is you're getting at 70 degrees centigrade, pretty high fluxes, 25, 27 kilograms per meter square per hour. Now the fluxes are somewhat lower at 10% because these were simple modules. They did not develop the type of modules which eliminates, the temperature polarization and so on and so forth. They just wanted to study, and yet you're getting a very significant fluxes, and we have a significant value of LEP. And there are all sorts of other studies that are going on in membrane distillation. I think I'll have other opportunities to present these to interested members of the audience at a future occasion. And I'd like to thank you very much for the opportunity to present this, and I'd like to acknowledge support from a lot of sources. The perfluorocopolymer research funding came from NJIT, NSF IUCRC program, and Compact Membrane Systems. The geo-based barrier membrane research came from Defense Threat Reduction Agency. Gregory Peterson was very helpful in testing some of our membranes. And of course, MAST Center has been supporting this particular project continuously over some time. And the membrane distillation research funding came over the years, over almost 15, 16 years, from U.S. Bureau of Reclamation, Office of Naval Research, ConocoPhillips, Chevron, United Technologies, MAST Center, and NJIT. And a lot of graduate students and postdocs have been extraordinarily useful, very helpful in carrying out this research. And we would not have been able to do these things unless these guys are there. They are literally everything. And with that, I'd like to conclude my talk. Hopefully, I haven't taken more time than I should. Thank you.
Thank you, Professor Sarkar. A very nice coverage, three distinct aspects of the membrane technology, the recent developments in that. Very well presented. And there are a few questions from the audience, from the participants. We have those questions with us. I will ask you one by one. The first question is, can we achieve separation of benzene and hexane using the fluoropolymer specified?
You said benzene and what?
Hexane.
Benzene and hexane. I don't think so. Not with this particular polymer variety CMS7. We have looked at this system. Hexane is a linear polymer. It is going to slip through very easily, and benzene and toluene is a similar thing. They will slip through. But there are other polymers that we are exploring, so we don't know what's going to happen with it. It's very much related to the free volume dimensions and the interactions with the particular solvent.
Okay. The next question is, are geomembranes permeable to 2.5 pm particle pollutants?
2.5, you mean you're talking about 2.5 micrometer particles?
2.5 particulate matter pollutants, yes.
If you are talking about particulate matter, nothing will go through your membrane. This is out of question. The gap openings, the defect openings are extremely small. So 2.5 micrometer is very large. It would be completely rejected.
Can we predict the radiation effects on the fabric prepared from the geomembranes?
This is a very important question. We have tested only UV. I doubt whether it can really block many of the other types of radiations that are available, and alpha and gamma radiations and things like that. We'll be studying these.
Okay. The next question is, can perfluoropolymer be used for separation of fluorine gas from a mixture of nitrogen and fluorine gas?
It depends on the particular fluorine gas that you're talking about. If you have say, a larger fluorine gas, then I think nitrogen is probably going to slip through and fluorine may not be able to slip through. But it depends on the dimensions. And of course, the uncertain item is the solubility or sorption. We don't know that.
So with this, we come to the close of your plenary talk. Very nice presentation, different aspects covered by you, recent developments. I'm sure it will encourage a lot of our youngsters, the participants who are hearing you this time. Thanks a lot.
Thank you very much.
After this talk, we move on to the next plenary talk for this session. Professor Ranil Vikramasinghe is the next speaker. Professor Vikramasinghe, he got his PhD degree from University of Minnesota in chemical engineering. He has been working in the University of Arkansas since 2011, where he currently holds the Ross E. Martin Chair in Emerging Technologies. Since 2020, he is the distinguished professor there. He has published over 200 journal articles, several book chapters and patents to his credit. He is very active in the American Institute of Chemical Engineers, and his research focus includes synthetic membrane-based separation processes and others. Professor Vikramasinghe is going to deliver the plenary talk on the topic of development of integrated electrocoagulation, forward osmosis membrane distillation for treatment of hydraulic fracturing flow back waters. Professor Vikramasinghe, 35 minutes for the presentation, and after that we will have 5 more minutes for interaction with the audience.
Thank you very much for the introduction. I think you can hear me now, right?
Yes.
Good. Let me just get this into slideshow mode. 1 second. Okay, thank you very much for the introduction. It's a great pleasure to be able to give this presentation. And it's the first time, of course, I think SESTEC has been held virtually. I was very much looking forward to coming to India and meeting many of the people I've met at previous meetings, but hopefully we can do that at a future meeting when the pandemic is over one day. But I also wanted to thank Professor Sarkar. He gave an excellent talk, an introduction to my talk, which actually leads off from the end of his talk. So I'm going to talk about development of integrated electrocoagulation, forward osmosis membrane distillation for treatment of hydraulic fracturing flowback waters. But basically, what I want to point out is the importance of developing an integrated process. As Professor Sarkar pointed out, I want to briefly first talk about the MAST Center and tell you a little bit about our center. We are actually in the University of Arkansas, which is located in Arkansas, which is here in the south central part of the United States. And we actually are in northwest Arkansas in a place called Fayetteville, which is bordered by Oklahoma, Kansas, and Missouri. And actually, someone from BARC, Arijit Sengupta, spent quite a bit of time with us, and I notice Arijit is on the call, so it's great to see him as well. The University of Arkansas Department of Chemical Engineering has quite a presence in membrane science and technology, since we lead the Membrane Science, Engineering and Technology, or the MAST Center, which is actually a very old center. It's an example of a National Science Foundation Industry and University Cooperative Research Center that was actually initially started in 1990. I want to point out that there are two things important about this center. Firstly, it's the Industry University Cooperative Research Center, so we have many industrial sponsors, and our mission is to provide value to our sponsors through quality research. Also, our other important aspect is that we are in the business of training PhD students. They are the major product from the center, and so we try to provide them with unique training opportunities. Our center research is actually broken up into various themes, and I'm going to talk about something that fits in with the water purification theme, but we are also very active in the area of biopharmaceutical processing, chemical separations, and membrane fundamentals. The center consists of 4 US-based universities, so University of Arkansas, New Jersey Institute of Technology, and Professor Sarkar is a very important part of the center, University of Colorado Boulder, and Penn State University. And we have one so-called international site where we collaborate with the R&D Center for Membrane Science and Technology at Zhongyuan University in Taiwan. But I told you it's an industry university cooperative research center, so it's important to remember that actually our sponsors are very important. And this is a list of our current sponsors, and you can see we have a range of leading biotech companies, membrane companies, water treatment companies interested in water treatment. So with that introduction to the MAST Center, let me move on to my topic. And the reason that this whole topic came about is that water is a very valuable natural resource, as we all know. Hydraulic fracturing produced water is highly impaired, and so it's very important to be able to treat this water. And what we find is a single unit operation is unable to treat the water. We have to have an integrated process. What is also important to remember is the amount of treatment you do depends upon the treatment goal. So here's a schematic representation of the hydraulic fracturing process. Basically, a well is drilled deep into the Earth's surface. It can go up to 1 kilometer in depth. Then it's turned horizontally and continues up to maybe another 3 kilometers in length. The oil and gas is in this shale-bearing formation that's highly impervious. So because of the very low permeability, conventional processes will not enable you to recover the oil and gas. So instead, what one does is one pumps water at very high pressure down this well that has been drilled, and the water contains various additives, propellant, which are basically sand particles, viscosity modifiers, surface tension modifiers, and surfactants, and so forth. And so this is pumped down here at high pressure. the water causes fracture of this rock formation. The propellant or sand particles go into these fissures. The pressure is released. We get hydraulic fracturing flowback water being recovered together with co-produced water. But the fissures cannot close because these sand particles or propellant prevent them from closing. So we've artificially increased the permeability of the rock formation, which allows us to then recover the oil and gas. I mentioned that the treatment depends really upon the treatment goal. So if the aim is to take this water and deep well inject it into a geologically isolated formation, basically the amount of treatment that's required is minimal, and it's known as primary treatment. Typically, the water comes up from the ground. It comes up with the oil. One takes off the oil. Then there's like a little layer of oil on the surface of the water, and that is usually addressed by oxidizing it with, say, chlorine dioxide, something like this. After which one goes to primary treatment, which typically is gravity separation centrifugation, and then the water is deep well injected into a geologically isolated water body. It's very important that this highly impaired water doesn't go and contaminate other water bodies, which could be used for beneficial purposes, for irrigation and so forth. If one wants to reuse this water to stimulate other wells, the amount of treatment required is somewhat more. One uses coagulation, flocculation, filtration, membrane separations, air flotation, electrocoagulation. Processes like this are used to remove additional components because, in particular, the water can cause corrosion of the drilling equipment. So you need to be able to remove these compounds before you can reuse the water for stimulating new wells. And then finally, if the aim is to take this water and discharge it into lakes and rivers, one has to treat even further, and typically evaporative processes are used for that. Today in the US, the major way of disposing this water is to truck it. So it's taken and it's trucked to a geologically isolated formation where it is deep well injected. The problem with that is one is trucking a huge amount of water all over the place, and so that's not very environmentally friendly. It's expensive, up to $10 per barrel, but most importantly, it causes earthquakes. And I can tell you that I live in Arkansas, which is a geologically very stable area, very old area. And when I first moved here, there were quite a few earthquakes. And the earthquakes come not so much from the hydraulic fracturing operation, but when one tries to re-inject large amounts of water into the earth. And so this project started off in the MAST Center, and the aim was basically to recover as much water as possible and therefore end up with a very, very high TDS brine or sludge that minimized trucking costs, because that was then going to be trucked and the water that was treated could be used for various possibilities. And so we started off by trying to determine the practical limit for the maximum total dissolved solids, or TDS, in the concentrate from membrane distillation. We worked with commercially available membranes and tried to find promising membranes. We then moved a little bit to explore forward osmosis. I'll explain why briefly in this presentation, as a possible unit operation for treating hydraulic fracturing, flowback, and produced waters. But I'm going to talk specifically about this combined electrocoagulation, forward osmosis, membrane distillation process. So we also brought electrocoagulation into the treatment process. I'll briefly touch upon an alternative combined process, and then I'll talk at the very end a little bit about some of the fouling resistant membranes we're trying to develop and why that is important in this application. So as was pointed out by Professor Serka in the earlier presentation, membrane distillation basically depends upon passing a hot brine solution on one side of a hydrophobic membrane, a cold distillate on the other side of the membrane. In all of this work, we use direct contact membrane distillation, but there are many other ways to run this process, and some of them we are looking at the moment, but in this work, we use direct contact membrane distillation. Since the membrane is hydrophobic, water cannot pass through the membrane pores, but water vapor can, and there's a vapor pressure gradient across this, especially if you have a high salinity feed stream. And the idea then is that the water vapor will pass through and be condensed on the distillate side. Now, it's often stated that the water comes out of the earth at a high temperature, and so the motivation is that you can try and make use of some of this low-grade heat to drive your separation process, and so therefore it should be attractive. Another point to remember is that the water vapor pressure of this brine solution will decrease with increasing TDS, or total dissolved solids. And here I show the vapor pressure of brine versus the vapor pressure of distilled water. If you compare that to something like reverse osmosis or nanofiltration, you find that the osmotic back pressure increases very rapidly as the salt concentrations increases in the feed. And therefore, processes like reverse osmosis and nanofiltration are not very effective here, because the amount of water you can recover for very high TDS brines is very, very small. But in membrane distillation, you still have quite a large driving force here, which is an advantage. So we looked at various membranes from our sponsors in the MAST Center, just to give you an idea. We looked at polypropylene, ECTFE, PTFE, PVDF, and then these superhydrophobic or coated PVDF membranes. This was the setup that we used. Basically, we have our membrane distillation cell here. We have our brine here. We used to maintain the brine at 60 degrees Celsius, and then we pump it from there on one side of the membrane while the distillate is collected and pumped on the other side. We can run this with synthetic produced water, in other words, take DI water and add brine to it, or we can run it with real produced water. We can run it where we maintain the same TDS in the brine tank, so we are running the feed in a recycle type mode here in a circle, and we add fresh feed from this tank, and if that were just DI water, we'll maintain the same brine concentration. Alternatively, especially with real produced water, we can run it such that we maintain a specific TDS here. So supposing the feed water had a TDS of 100,000, we want to run this at 150,000. We would then concentrate till we get a brine of 150,000, and then we run in a feed and bleed type mode, where we take away high TDS brine at the same time adding new produced water at 100 TDS, and we can balance this so that we maintain a TDS value of say 150 or whatever we like. So we tested these membranes. We tried to take them to the limit. In other words, the point at which you get breakthrough. So if you are testing them with, say, DI water with sodium chloride, which is how we tested them here initially. This is a DI water starting off at 100,000 ppm sodium chloride. The only thing that can happen is you can get scale formation on the membrane surface. There are no other foulants present. And at some point that happens. It's shown here where it occurs. And when it does occur, if you look at these blue triangles, that gives a permeate flux. The permeate flux suddenly increases, and the conductivity given by the right-hand side y-axis also suddenly increases because we've got breakthrough. So we've got water passing through the membrane pores and not water vapor. We actually tested a number of different membranes, and you can see the feed concentration at breakthrough is very similar for all of them. But what is important here is that we basically decided to use the ECTFE membrane since that membrane was just much easier to handle. And this is what the membrane looked like after we reached breakthrough point, and you can clearly see that some scaling was occurring on the membrane surface. And these are some of the properties of the ECTFE membrane. You can see the nominal pore size was 0.2 micron. It is hydrophobic. The contact angle is about 130 to 140, and some of the other properties of the membrane are given here. Let me on. Now, one of the things we noticed, and I'm going to have to power my computer into the power because I noticed the battery is getting low. One of the things we noticed is when we use real produced water, you can see that there is a decrease in flux, and this decrease is rather rapid, as you can see. So that is due to fouling of the membrane. So two things can happen when we run this process. We can get membrane fouling and we can get breakthrough, and both of which lead to a severe degradation of performance. Here I compare the result for, say, an artificial wastewater, basically deionized water containing sodium chloride, and you can see the decrease in flux is given by this red curve, and a lot of it is also due to the fact that the driving force is decreasing as you start to concentrate the feed solution. But on the other hand, if you look here, you can see that when you have a real produced water, the decrease in flux is much, much more severe. And at the bottom, we see the membrane. This is for real produced water. This is for the synthetic water after membrane distillation. And clearly, you can see a significant amount of fouling is occurring. So this leads to the first major point, and that is that whatever you do, you're going to have to pre-treat the feed. It doesn't matter what sort of membrane you design, feed pre-treatment is going to be essential. And really, there are three contaminants: there's suspended solids, dissolved solids, and organic compounds. Remember that this feed stream contains surfactants and other sorts of polar and non-polar organic compounds. The membrane has to be hydrophobic because you don't want water passing through. So it has to be oleophobic as well to prevent absorption of oils. But it's more complicated than that because you also have surfactants and low surface energy compounds. And so simply lowering the surface energy sometimes doesn't help. And so pretreatment is essential to try and remove some of these organic compounds. There are various possible pretreatments that people have looked at. We chose to look at electrocoagulation. So electrocoagulation is very similar to coagulation, but it was advantageous for us because electrocoagulation, all you need to do is change the electrodes. And so if you imagine running this somewhere in an oil field, the amount of material you have to transport is not much, just the electrodes, not a whole lot of coagulant. And so electrocoagulation was considered a process that would be quite feasible in these oil fields. So the electrocoagulation process was used for pretreatment. Electrocoagulation system consists of a reactor. Now, in this early work, we used aluminum plates, which I show here, and we used a DC power unit, as shown here. In more recent work, we actually have advanced this quite a bit. It turns out with electrocoagulation, you don't have to just use aluminum. You can integrate these. You can have aluminum and iron, and so forth. And there are benefits to that, especially depending on the type of contaminants you have present. You might actually have better, more efficient removal of certain flux if you have iron. And what is also important is that the flux densify quickly and are not light flux that are not easy to densify and remove. And so we have now developed a process where we use a mixture of electrodes. The other important point is that actually for a real process, for a practical process, you would need to use an AC power source because you'd want to keep switching the electrodes, because if you don't, you can get passivation, an oxide film forming on these electrodes, and that actually will lead to a reduction in the generation of ions, which are what you need to flocculate your organic compounds. So if you're using aluminium at the anode, you get aluminium ions formed. At the cathode, you basically get hydrogen gas formed. The hydrogen gas is important because as it rises, it helps in the flocculation process. In solution, the aluminium ions actually very soon start to form these aluminium hydroxide species, and those are the ones that are then able to capture the organic compounds. They absorb on the surface and you form these flux. Initially, the flux are very light and low density. They rise to the surface, they start to densify, and then they fall down again and settle at the bottom. And so what our aim was to recover the clear water, the treated water after flocculation. Now, in this early work, again, what we did is we used electrocoagulation. We induced flocculation or coagulation. We then waited, let it sediment, basically. So we waited, and the sedimentation time can be up to 8 hours or more. So in that sense, it's not a very practical process. You have to wait a very long time. So I'll also give you an example of an alternative process as we go through this. But in this work, we waited for sedimentation. We took the water, and then we ran it into the membrane distillation system. This is an example of the actual produced water, and below that, you see the produced water after electrocoagulation. And for the specific conditions we used here, we got very efficient removal of the total organic carbon, you can see here, of the total suspended solids and turbidity. So this water electrocoagulation was very successful in removing the compounds you want to remove. It's not designed to remove dissolved ions. The TDS doesn't change much. So shown here is the normalized water flux versus permeate volume. The blue circles are basically one. This is a synthetic water, basically say salt in water. The green curve here is for the real produced water after electrocoagulation, and the red triangles are for the produced water without electrocoagulation. And you can see here that what happens is you increase your water recovery over a certain period of time because the fluxes are higher. But importantly, by suppressing fouling, you try to suppress wetting of the membrane. Now, it turns out that it's unlikely you would run this in a single stage. So supposing your feed water in this example is coming in at 150 ppm or 150,000 ppm gram per liter. You might decide to run the first stage at, say, 200 gram per liter, 200,000 ppm, the next stage at 250,000 ppm, the next 300,000 ppm. And then you can recover clean water or treated water from each one of these stages. And by doing it in a staged process, one of the good things is then you can tune the properties of the membrane for each stage, because as you start to increase the concentration of dissolved species in here, naturally the tendency for fouling is going to be greater and the water fluxes will be less. So you can tune the pore size and morphology by doing this staged approach. And then after each stage, the brine was sent to the next stage and we recovered more water. Now, you can run a staged process like this, but it turns out you're going to have interstage heating. But if you remember at the start of this talk, I said one of the motivations for membrane distillation is that the water comes out of the earth at elevated temperature, so you can capture this energy to use it to drive the separation. It turns out that this may not be as simple as it seems for a few reasons. One reason is that you've already seen that there's quite a bit of pre-treatment before you get to membrane distillation. So firstly, it comes out, there's a chlorine dioxide treatment, then it goes, in our case, through electrocoagulation, there's a long sedimentation time. So by this time, the heat energy is all lost. The only way you can recover it is if you do heat exchange right at the very start of the process, and that's a little problematic because the water is highly impaired. You can cause corrosion of your heat exchange equipment, so it may not be that feasible. So in reality, it might be more difficult to make use of this waste heat. Now, the MAST Center sponsor that was involved in this project was actually particularly interested in recovering natural gas. And so for them, having a heater, as I show here schematically, was not a problem. And so we could have heat exchange in each stage. Remember, the feed temperature drops as you go through this module because for two reasons. I'm using direct contact membrane distillation, so therefore there is heat loss across the membrane. In addition to that, you have to have vaporization of on the feed side, condensation on the distillate side. So there's an energy transfer involved in that. But you can have this interstage heating, and again, that makes these different stages more efficient rather than having like one big stage. I said I'd tell you about an alternative process. So more recently, and that's given in this recent publication here, we have looked at using electrocoagulation followed by microfiltration rather than sedimentation, and then going to membrane distillation. And what we find is that actually we can run this into a microfiltration system relatively quickly, basically directly from the electrocoagulation process. And that allows us to much more rapidly treat the water and try to develop a continuous process. But that's another option. Okay, so I said I'd mention forward osmosis. So we developed this process to use membrane distillation integrated with electrocoagulation. But it's claimed in the literature that forward osmosis, many papers claim that it is less fouling since you don't have a hydrostatic pressure force. It's all an osmotic pressure force. The reality is I can tell you that when you're trying to do forward osmosis, you will get fouling, especially for these hydraulic fracturing flowback waters. So we began by trying to just look at transport across the membrane and solve the convective diffusion equation. So if you assume the simplest case, you have a draw solution consisting of, say, deionized water with salt, and your feed is just DI water. So what you'll have is you have an external concentration polarization boundary layer on the draw solute side. You have internal concentration polarization, and then some sort of resistance to mass transfer through the active layer. If we now have a salt solution on either side but at different concentrations, then the concentration profile is similar, except now you could have an external concentration polarization boundary layer on the feed side. In our case, you also have this fouling resistance because we do observe fouling, and again, we do have to use a pretreatment step, and we use electrocoagulation. So basically, we came up with this equation to try and predict our results. And so here are some results that we obtained. This is water flux versus recovered water volume. You can see here the red triangles are for the actual produced water without any pretreatment. Then we have squares and circles representing various pretreatment conditions. And finally, the black diamonds are for the synthetic produced water. And the dashed line was our model, where we assume that it's a synthetic produced water, so it doesn't have any fouling component. You can get scale formation, that's all. Okay, so here's the process we were wanting to explore. We take our feed, our produced water. First, we'd run it through an electrocoagulation unit, and then after that, we'd take the clear liquid to a forward osmosis step. So in forward osmosis, what happens is you have the feed on one side, you have your draw solute on the other side. Now, this will only work for produced waters that don't have exceedingly high TDS values. So if you had exceedingly high TDS values, it's going to be very difficult to find an appropriate draw solute to be able to recover the water. So what happens then is the draw solute is diluted, and the diluted draw solute is taken to membrane distillation unit. And in the membrane distillation unit, we're going to regenerate the draw solute, basically concentrate the draw solute, and then we'll recover clean water. So this is the process. We tested it with two different produced waters. I show the results here for these produced waters. One was from the Fayetteville shale, the other was obtained from the Marcellus shale. If you look at it, the main difference is in the TDS. So the Fayetteville shale had only about 11,340 milligram per liter, and the one from the Marcellus shale was about 57,000 milligram per liter. And I also show values here of the TDS and so forth before and after electrocoagulation. And so you can see that if you consider after electrocoagulation, the values have all dropped significantly for the total organic carbon, for the total suspended solids. The TDS won't change much because electrocoagulation is not designed to remove inorganic ions in solution. So we ran our process as follows. Let me show you results first for the water from Fayetteville. So this is the much lower TDS. So we start off here in the first run. We run our forward osmosis step. We start to dilute the draw solute, so the permeate flux starts to decrease. We have to stop then and run our first membrane distillation step, where we regenerate the draw solute. Then we go back and run the second forward osmosis experiment, then the second MDN. In that case, we keep going, and we manage to recover quite a lot of water, as shown here. When we ran the process with the Marcellus shale, we ran into a slight problem. So in the previous case, we used about a 2 molar sodium chloride solution as the draw solute. This time, because we have a much higher TDS water, we had to use a 5 molar sodium chloride solution. And in doing that, we see here first the first forward osmosis step, the draw solute is diluted, the permeate flux drops, we go to membrane distillation, we regenerate the draw solute, we go back to forward osmosis, then back to membrane distillation. But when we got to this very last stage here, unfortunately, the membrane failed. We had a breakthrough. As you can see, the TDS rapidly increased. So the way around that was as follows. We used two membranes, and I told you a staged process is always something to think about. We used basically, as you can see here, we used our PTFE membrane to concentrate the draw solute to a certain point, and then after that we used a different membrane, a PTFE membrane, to then concentrate the draw solute to the final amount, and we did that so we can get up to 5 molar sodium chloride. So here's the process. We first run forward osmosis to a point, then we start to regenerate the draw solute with the first membrane, then with the second membrane, run forward osmosis, then regenerate the draw solute, first membrane, second membrane, and so forth. And you can see this time the conductivity of the draw solute doesn't increase much. Okay, let me move to the last part of this talk in the last few minutes that I have. What I hope I have shown you from that is that actually the major challenge here is designing a membrane that is going to be fouling resistant and resistant to breakthrough of the water. And that's a tough problem because the membrane has to be hydrophobic to prevent water from transporting through the membrane pores. But we also have polar and non-polar organic compounds, so it should be oleophobic. Otherwise, you'll get these compounds adsorbing, and if they adsorb, then they can actually change the surface properties and you'll get breakthrough. But what's even more complicated is that we have surfactants and other low surface energy compounds present. So simply lowering the surface energy of the surface may not be sufficient because surfactants can still adsorb. And so, in fact, there's a lot of work looking at trying to design surfaces that have got a certain amount of roughness. So we don't just have an enthalpic barrier to adsorption, but also an entropic barrier. So we decided to work in this project anyway with electrospun membranes because they have a rough surface. And so we make three membranes here. We have a base PVDF membrane, right? Electrospun PVDF membrane. We have PVDF-CF, which is PVDF containing this quaternary ammonium group, and basically in the dope. And then we add silica particles by electrostatic interaction, and then we dip coat with fluorine, creating an omniphobic low surface energy surface. The final, that's shown by this red schematic here. And then the green is a second electrospun membrane. So this is a bilayer. And basically this membrane was alkaline treated, followed by grafting zwitterions from the surface. So this top surface now is hydrophilic. It faces the feed stream. So we're trying to prevent organic compounds from adsorbing on the surface. The lower layer is hydrophobic, and that's to prevent water from going through the membrane pores. So let me show you some results quickly. These are some contact angles that we obtained. The first panel here gives the water contact angle for the PVDF and the PVDF-CF membranes. They're highly hydrophobic, as you can see here. The PVDF-BZ, which contains the grafted zwitterions, is of course very hydrophilic. We looked at ethanol contact angle, the PVDF membrane wicks. The PVDF-CF membrane actually is still quite resistant to ethanol, but the PVDF-BZ membrane, which contains the zwitterions, actually is quite easy for ethanol to wet this membrane. And then finally, what's important is the underwater oil contact angle, because after all, it's dissolved organic compounds and oils that are going to adsorb on this membrane surface. So what's important here is the PVDF-BZ membrane, which is the one that contains our zwitterionic groups and is going to face the feed stream, actually has a very high underwater oil contact angle. The PVDF and PVDF-CF membranes have a very low underwater oil contact angle. These are some SEMs of our fibers. The left panel is the PVDF nanofibers. The middle one is the PVDF-CF, which you can clearly see the small silica particles on the surface. The fibers are a little bit narrower than the others, and that's probably because we had a quaternary ammonium in the dope. So there's going to be a greater charge, and so we had to use a higher voltage when we're spinning these membranes. And then finally, here are the PVDF-BZ, and you may be able to see tiny white dots, which probably represent the zwitterions on the surface. Now, let me show you some performance data. So in this figure, what we want to do is do two things. We want to see how resistant these membranes are to wetting and how resistant they are to fouling. So the top panel here shows the normalized water flux for the three membranes, normalized to the original water flux. And so all three membranes therefore start off with the blue symbols. That's the normalized flux read using the left-hand side y-axis, and they start off at 1 because we're basically normalizing to the initial flux. The right-hand side y-axis gives rejection, and you can see the rejection starts off at close to 100% for all three, PVDF, PVDF-CF, and PVDF-BZ membranes. At some point, in fact, after 2 hours, you can see we changed the challenging solution from DI water to DI water containing 0.1 molar SDS. And what happens is that almost immediately, we start to see that the flux for the PVDF membrane starts to increase rapidly. The rejection starts to drop rapidly, which suggests, therefore, we got breakthrough in this membrane. The other two membranes were stable. There was no change. We then looked at what happens if we add some oil to the water. And so here we don't have surfactant, just oil in this panel B. Again, same idea. We start off with a normalized flux of 1. You can see the flux decreases for all of the membranes. So we are getting adsorption and fouling by the oil, but we don't get breakthrough. The circles represent the PVDF-BZ membrane, which has the zwitterionic surface that's facing the feed, and there's the least decrease in flux for that. The other two show much more rapidly in flux, but there was always about 100% rejection, so there was no breakthrough for this membrane. Now, the third panel here is when we try to model a real produced water, so we have both SDS and crude oil. So if you look at the fluxes again, they start off at 1, but if you look at these blue open squares, that's the PVDF membrane. This flux starts to drop a little bit and then suddenly goes up. The drop is because we're getting adsorption and fouling of the membrane. It suddenly increases because then at some point we have breakthrough. And if you look at the conductivity, the same thing happens, or the rejection. You start off near 100% right on the right-hand side y-axis, and suddenly it goes down when you start to get water going through. For our two modified membranes, the CF and BZ, you see that they have good water fluxes. The decrease is not great. They are able to reject and they are anti-wetting. And the flux for the BZ membrane is higher, the one that contains bitter ions. And in both cases, you have close to 100% rejection of salts. So finally, we tested it with a real produced water. This real produced water you can see here has a very, very high TDS of 245,000. Total organic carbon is high. Total suspended solids are high. And this is a breakdown of the inorganic compounds. So look at what happens. When we look at the top panel, this is what happens with the PVDF membrane. We get almost immediate breakthrough. The conductivity or the rejection starts to go up, the flux drops. Panel B here on the right-hand side is for the PVDF CF membrane. We don't see breakthrough. We start to see a decrease in flux and a slight increase in rejection, but we don't really see breakthrough yet. For the BZ membrane, same sort of thing, curve occurs. However, actually, the actual value of the flux is the normalized flux. The actual flux is higher. And so let me then, I think I'm out of time, so let me conclude. What I show you here is that membrane distillation enables concentration close to the TDS limit if you can prevent fouling and breakthrough of the membrane, to close the solubility limit. The treatment of hydraulic fracturing flowback water is feasible. We show that pre-treatment is essential. Electrocoagulation combined with membrane distillation provides high water recovery, and a staged operation is important. And then I showed you some examples of integrated process. But what's really important is developing a high-efficiency membrane that prevents fouling and breakthrough, because after breakthrough, it's very, very difficult to regenerate the membrane. Finally, I'd like to acknowledge various funding sources for this work. There are a number of people that have worked on this project, but the two most recent are Mahmoud Jabour, who is a PhD student, and Yushen Chow, who is a postdoc in my group. So with that, I thank you very much for your attention. And again, it was a great pleasure to be able to attend this meeting. Thank you.
Thank you, Professor Vikramasinghe, for this excellent presentation on the integrated approach, taking advantage of electrocoagulation, forward osmosis, and membrane distillation. I'm sure that all the participants enjoyed this talk and learned a lot from this. We have a few questions for you from the participants. I will ask you one by one. How is the area geology important in case of hydraulic fracturing?
The area geology actually is very important, because that will determine what sort of contaminants you have. So the inorganic contaminants that you have will be affected by the geology. In addition to that, you can get organic compounds and things from the rock formation coming in. The components that are added will tend to be the same. All of the viscosity modifiers and so forth, their proprietary will be similar. But the geology is important. Another important thing is that you can also get things like volatile organic compounds like ammonia present. That depends also on the geology. And volatile organic compounds will not be rejected by membrane distillation because they are volatile. They will also pass through into the distillate. So the geology is very important.
In case of electrocoagulation technique, what is the time duration required for getting efficiency levels for TDS levels?
So electrocoagulation that we showed here, we ran for something from about 1 to maximum about 10 minutes. You should not need to, that was the batch process. In a continuous process, we also try to have a space time of around 10 minutes. Anything longer than that starts to make this not very feasible. And also you have very high energy costs and you start to use your electrodes a lot. So it's fairly quick. That's a quick process.
And for this integrated technique, how expensive is it?
So we have not done a cost analysis, but I can put it to you this way. The electrocoagulation process actually is quite cost effective when you compare it to other sorts of pretreatments. You're replacing electrodes, and if you optimize the process, so that you don't get passivation electrodes and so forth. It's the electrode cost that's the disposable cost. And in fact, that's quite reasonable. What comes next? So we initially looked at sedimentation. The downside there is you need large sedimentation areas. Of course, that's relatively cheap if the land is available. But if you want to speed it up and use microfiltration, then there is a cost associated with the membranes. We have been looking at ceramic membranes for this process, which seem to be very robust and have a long lifetime. So that has also been quite reasonable in terms of cost. But I can't give you an actual number because I haven't done the analysis. But certainly with our industrial partners, the process we propose seems to be quite competitive.
What is the voltage used for the electrocoagulation process?
We have looked at voltages of about 10 to 20 volts. You can run it in two ways. We have tried to maintain a given current, and then the voltage, of course, changes because as the number of ions in solution changes, the voltage changes. The voltage you use also, if you put in a constant current, will also depend upon the TDS, right? Because you've got ions in solution.
Professor Vikramasinghe, one question, last question from my side. You showed the results from two particular areas of the flowback waters being
Yes.
treated in this integrated approach. Is it the methodology which you are presenting here and the actual application on flowback waters from some other regions? One has to tweak each of these processes to get the most optimum result.
Yes. So depending on what's in the water, you will have to tweak your electrocoagulation process, right? Because you want to optimize that. So if you think of just chemical coagulation for water treatment, the dosage you use, so forth, is highly variable depending on the pH of the water, and various things like this, the hardness, so forth. Electrocoagulation is similar. It turns out, though, that actually electrocoagulation is a little bit more robust than, say, using alum or something like this. It's actually, there's a bigger window, which we could discuss if you're interested, where you can actually get very good flux formation, because you want to get flux formed quickly. Whether you're using sedimentation, microfiltration, you want to get flux formed quickly and they need to densify very quickly. So yes, you need to tweak it. So you need to do some sort of like jar testing, some sort of the equivalent of jar testing to determine optimum conditions for the electrocoagulation process. And you determine that based on your limits for membrane distillation, right? Because you want to make sure the membrane distillation process is robust and you don't get failure of the membrane. So you'll have a certain maximum allowable, say, total suspended solids, total organic carbon, and so forth. Another thing I should point out that there are both dissolved and suspended organic compounds. There are colloidal particles present and there are dissolved organics. It's the dissolved organics that tend to be very problematic that you have to remove very carefully.
Thank you, Professor Vikramasinghe, for the excellent presentation. Thanks a lot.
Thank you very much.
So with this, we close the session, first session of today's, and we will be starting the next session at India time 11 o'clock. Thank you.
Thank you, Professor K, for chairing this session. Now we will have an e-break and will meet again at 11 a.m. IST. I request all the participants to switch on their video so that one screenshot can be taken. I repeat, I request all the participants to switch on their video so that one screenshot can be taken. Thank you all. We will meet again at 11 a.m. IST.